Well, as Ehua said before, time goes fast when you're enjoying yourself, and this conference is rapidly drawing to a close. I spent some time thinking about what I should say at this Stein Memorial Symposium, and decided in the end that what I'd like to do is to give some sort of idea of how Stein's work has affected me as a sort of microcosm of how Stein's work has affected people in general. And it must have been incredibly pleasant for him to see how many people have developed his ideas in how many amazing different ways. And it's been stunning during this meeting to see many of them talked about by young, enthusiastic people who are taking the subject way away from how it began. I failed to remember a quote of André Gide's once on a similar subject, talking about writing, saying that the essence of genius was to write things which can be interpreted in many different ways later on, even though the author himself didn't have those particularly in mind. And somehow one feels Stein's method fills that description extremely well. So, yes, what I'm going to talk about is just a selection of applications of Stein's method that I've come across in my now rather many years of working in Stein's method. So this is the title of the paper that started it all from the 6th Berkeley Symposium. Gesine already mentioned that about line 3 he was saying that actually this paper wasn't really a finished work and should be treated as just steps on the way, and he was unsatisfied with various aspects of it. But I think it's had such an amazing success in later years that we must say that even if that's the case, it was still a stroke of genius. And here's corollary 3.1. X1, X2 is a stationary M-dependent sequence of random variables satisfying 3 conditions. My memory is the first one is the mean should be 0. The second one is that the variance of the sum divided by n should be converging, and it should be converging to this C. So 3.3 is the only condition which isn't in some sense obvious, and that was, I think, that 8th moments exist. But then under this assumption, you have a Berry-Essene approximation to the distribution function with a rate n to the minus a half. And you probably can't cast your mind back that far, but some of us can, more or less. And apart from the fact that one forgets things in old age, the thing to remember is that n to the minus a half was amazing and shocking, that people have been working hard to get the Berry-Essene theorem for stationary sequences, and they weren't at n to the minus a half until this paper came along. So it wasn't just a new, original, amazing technique, but it was also a new, original, and amazing result. So let me give you one application of this, which comes from an ANMath stat paper in 1957. So let's say it would have been an application had they known about Charles's paper from some years later. And this concerns the number of maximal points in a sequence. So you have a sequence 1 to n, and on each of these points you have a random variable, and I believe they're meant to be independent, IID continuous, so you've got values at all these points doing something. And then you count the number of maximal points. And maximal point is defined as follows. If you take a particular index here, let's call it R, and then here you have R minus K plus 1, and so on, and somewhere up here you have R plus K minus 1. So you call R a maximal point if it's, well, a K maximal point. R is a K maximal point if the value at R is bigger than either all the values in the K interval here, or all the values in the next K interval containing R, and so on up to here. So you've got, whatever it is, K intervals to look at, and if it's the biggest in any one of those, then it counts as a maximal point. So if you looked at a sequence of numbers that was just going up steadily, then they'd all be maximal points because they'd all be bigger than the ones coming previously. And I think this was used as a test in statistics for testing some sort of regular behavior of functions against randomness. So suppose you want to count the number of maximal points. What can you say about its distribution? Well, because these intervals that you look at are of bounded length, it's clear that the value at R is independent of the values for other values R dashed, which are further away than, so that the intervals don't overlap, which I think makes it 2k minus 1 dependent. So you have a 2k minus 1 dependent sequence, and so you can apply Charles's result. I mean, the random variables are indicators. You should check that the normalized variances do indeed converge. I've called the limit sigma squared here, but it was actually c in the previous corollary. And therefore, the conditions are satisfied, and you've got a convergence rate of order n to the minus a half. Now, the actual results in the Anmath State paper of Austin, Fagan, Lair, and Penny were much more complicated. I mean, they did a detailed combinatorial style analysis, got a generating function for the distribution, which they're able to reproduce for n equals 1, 2, 3, 4, 5, 6, and 7. But they give you a formula involving a derivative at each stage. You go from n to n plus 1, you have to differentiate an expression once more, which presumably with modern computer algebra would actually be able to give you the exact distribution. Nonetheless, for practical purposes, knowing that it's approximately normal with an error, I think is roughly what you would like to know best. This slide is merely to say that this is where I first found out about Stein's method when I was reviewing Louis Chen's 1975 paper, the Zentralblatt für Mathematik, and it's an illustration of what life was like before TeX. Please note that Stein's name is spelt with blanks in between for emphasis. It's marvelous, isn't it? And things really were underlined in those days. The typeface looks a little wiggly, but actually, you know, when you read it on Zentralblatt nowadays, even in electronic form, it's not particularly pretty. The interest of this was that I used to write reviews which were 3 sentences. I mean, I gave myself 3 sentences to explain what the paper's about, and this was so important that it went on for a page. So here's an example. Something that I used to work with a lot, and still actually do from time to time, is Markoff population processes. And these are processes which are very useful for modeling biological phenomena, and you can think of a point sitting in RD typically, which makes jumps to some sort of local point. And when I say RD, I mean ZD. They tend to be counts and live on integers. Here I've got a one-dimensional example. This is some sort of birth process. At point J, you think you have J individuals, and each of those J individuals has tendencies to reproduce. So all the rates for moving from J are proportional to J, and you might have 1 child or 2 children or 3 children. So it's not what the mathematicians now call a birth and death process, because it's not got jumps necessarily just 1 upwards, but the deaths tend to happen 1 by 1. Now, if you didn't have the factor here, you would have a Markoff branching process, and then the process would either go to infinity with probability, well, with positive probability, or it would be absorbed in 0. It always has a chance of being absorbed in 0, and it's absorbed in 0 with probability 1 if the right condition for growth is not satisfied. The branching process is going to die out. Now, the difference with this particular process is that we have some sort of factor in here, theta j over n, multiplying the death rate. So you've actually got a quadratic death rate, and because quadratic beats linear, eventually if j is big enough, the drift is downwards rather than upwards. So unlike the branching process, it doesn't either diverge to infinity or go to zero, and this makes it a much more useful model for modelling biological populations. And you see that this factor is rather small until j is comparable to n, so you think of somewhere around about n, in fact more precisely, where the drift becomes zero, as being the place at which the typical values of the process will be. And at that sort of level with j about n, all these transitions are happening rather fast. They're all happening at a rate of order n. On the other hand, they're still not going very far. So you're in the circumstance where you've got a lot of small transitions making up the behavior of the process. And this makes it plausible to suppose that you have things like laws of large numbers, central limit theorems, and so on. And in the early 70s, this was proved by Tom Kurtz in a succession of papers with ever better results. But the basic result is that if you divide the population size by n, then you have a deterministic or fluid behavior, and around that, if you renormalize up by square root n, you get a diffusion process. Now, these are results which are based on finite time intervals, and I was interested in looking at equilibria where you really want to not have to worry about the finite time interval. So, okay, it's a very specific process. You can write down a generator. It's a jump process. And you can compute what the drift is. Mu is the sum of RPR, which is the sort of birth pressure combined with the rate lambda. And it's balanced by a drift from death. So if you think about where this becomes zero, it's where 1 plus theta x over n is equal to lambda mu. So that's roughly where the process should stabilize. So let's call that little x bar. It's equal to lambda mu minus 1 divided by theta. So you think of lambda times mu as being bigger than 1, so that the process is trying to go to infinity, but for the quadratic depth. Well, okay, we think now that there should be some nice distribution for the difference between x and x bar divided by square root n. That's on the capital level. So this is order square root n fluctuation for the equilibrium distribution. So you rewrite the generator h hat of y in terms of y, so with h hat of y instead of h of x bar plus y square root n, and you write the formula down, and you expand in powers of square root n. So these differences here and here, provided the function h hat is smooth, the first difference is going to be order 1 over square root n. The x bars are going to be like order n, so the biggest terms are order square root n, then the next terms are order 1, and so on and so forth. And it's routine Taylor expansion to see that the n to the half terms cancel because we're doing it around equilibrium. The constant terms give something which doesn't cancel, and the rest of them give things of order n to the minus a half. But the bits that don't cancel and are of order 1 have y times h dashed of y and h double dashed of y. In other words, we have the Stein equation for the normal presented to us with constants theta x bar and half lambda x bar. And we know that the expectation of a h hat of y is 0 in equilibrium by Dinkin's formula. So we're in business. We immediately have the possibility of using Stein's method. And so when I was looking at this problem, I was able to use this to prove, in particular, Berry-Esseen result with rate order n to the minus a half, so for Kolmogorov distance, as well as smooth functions. Then, of course, time goes by, and sometime in the 2000s, I've been working with a particular crop of PhD students then, and we'd been interested in translated Poisson approximations, so you can guess that Adrian was one of them. And I looked at this problem with another of my students, Sander Sokol, and we did the same thing but now in total variation. So you're going to do much the same sorts of things, but the behavior is a bit different because you can't divide by square root n at all and stay within the integers. So you have to look at, as it were, Newton expansion about x bar, where you really look at differences of the function rather than derivatives, and so on and so forth. So life gets a lot more complicated. You have to be careful of the errors. And whereas when you go on differentiating, at each stage you get another factor 1 over square root n, with the differences, this stops happening after the first or the second. And so you have to use other things to make sure that the remainder terms are small. And you need some smoothness in the underlying distribution of x, and you have to establish that. So this is something that tends to come up in total variation approximation. You get nice normal-like things to compute, to quantify the error, the things that you would have in Berriesian bounds, and then you have to have something from smoothness as well. So that was the case here. And then another 10 years later, Ehua Shah and Malvina Luchak and I were working on total variation approximation near the Gaussian limit for sums of integer-valued random vectors. And then it turns out that all this Markoff population stuff was rather interesting, rather useful, because we have a Stein operator for multivariate discrete approximation, but it isn't a generator in higher than one dimension. So we can't, I can't even solve the Stein equation with that generator, let alone say anything about the properties of the solution. But this sort of Markoff population process you can define in any number of dimensions, and you have a well-defined generator. So it turned out that we could find, as it were, for an arbitrary covariance matrix, for the discrete normal, we could find an operator in terms of a Markoff population process, which was sufficiently close to our actual discrete multivariate operator that you could use that for the computations and for the solutions as well. So it turns out that the Markoff population processes were actually very useful for multivariate Stein approximation in total variation as well, which is nice. Now there's another thing that came out of this particular study, which again involved Stein's method coming in, and that was the following. I'd protected against having a process which gets absorbed in zero eventually by having a transition out of 0 to 1 at rate epsilon. Because if you don't have that, then the set of states, the natural numbers, is transient, and the process will get absorbed in 0 with probability 1. So the equilibrium distribution is actually point mass on 0. This doesn't describe what you observe biologically, where the process stays around its carrying capacity of order n for a long time and is only absorbed through chance. Maybe takes exponentially long to be absorbed. So in principle, this epsilon comes into the equilibrium distribution you get, but as far as the normal approximation is concerned, you don't see it. Now, in the 60s, Darach and then later jointly with Sunita were interested in such problems where you have Markoff chains with an absorbing state, but the process in some sense can stay around for a long time, maybe, maybe not. In any case, you can look at the distribution of the process given that it hasn't yet been absorbed in 0. And they described something called a limiting conditional distribution, which I denote here by pi tilde. And their view was that you should use this to describe the effective equilibrium distribution rather than putting in a little bit of drift into the process at rate epsilon at 0. And I should say that the idea of putting a bit of drift out of the absorbing state, a bit of rate out of the absorbing state, was introduced by Bartlett in his 1956 monograph on population processes, and he took it as self-evident that that's going to make no difference at all to what's happening. Dirac and Sunita were very disparaging about this idea. They said, look, the problem doesn't contain an epsilon, the answer shouldn't contain an epsilon, so this is obviously the wrong thing to do. And in that sense, that's fair enough. But there are problems with recasting the problem in this form. First is you don't know what the eigenvalue delta is. So you've got to do computations to find that, and these computations may not be at all easy. And the second is that after you've done that, you have to find the eigenvector, and again, that can be a complicated business. I mean, it's much easier in practice actually to run the process, look at the effect of equilibrium and see what that looks like, rather than go through this problem. What's more, even in mathematical terms, this isn't necessarily easy, because whether or not there exists such a quasi-stationary distribution depends in some fine detail on what the jump rates of the process are. And if you started modifying the ones that I had on the transparency up and away towards infinity in places where the real process will never reach, you could actually change this whole problem to one in which there doesn't even exist a quasi-stationary distribution. So it sort of seemed a nice idea to try and rehabilitate Bartlett's idea. So now put an epsilon underneath both the generator and the equilibrium distribution to reflect the value of epsilon that we've chosen for going from 0 to 1. Then this generator A epsilon h equals f minus pi epsilon f, the Stein equation associated with it, you can solve it. You know what the process is, you can do a lot with the solutions, and in particular you can see that the infinity norm of h epsilon is bounded by the infinity norm of the function f times log n plus 1 over epsilon. These bounds have to do with the amount of time taken in certain, the process travelling to certain sets, and so the 1 over epsilon is the average time it takes to get out of the origin, and log n is something to do with how long it takes to get to equilibrium in a loose sense. So for any epsilon such that 1 over epsilon is less than log n, you're not going to notice the epsilon in comparison to the log n. But it's really better than that. So now if you want to work out what the expectation of f is under the pi epsilon dash distribution, then all we have to do is put that on the left-hand side here and take expectations, and we've got the right thing on the right-hand side. So the total variation distance between the epsilon dashed equilibrium distribution and the epsilon distribution is going to be given by applying pi epsilon dash to a epsilon h epsilon. And again, from Dinkin's formula, pi epsilon dash applied to a epsilon dashed h is 0 for all h. So you take 0 away from the right-hand side, and you find that the total variation distance is going to be bounded by the expectation of a epsilon minus a epsilon dashed h epsilon of x. So that's under the epsilon dash distribution. But the nice thing is that the two generators differ only in one place, and that's in the transition out of 0. One of them goes at great epsilon, the other goes at great epsilon dashed. So this expectation is the probability under epsilon dashed of being in 0 times something that's of order 1. So maybe there's a norm of h of order 1 over epsilon. And that tells you an enormous amount, because the probability of being in 0 for any epsilon dashed which is at all big is exponentially small in n, which you can prove by Lyapunov arguments. So actually, it says that the difference between the pi epsilon dashed and the pi epsilon is only visible at orders exponentially small in n. So think of when we're doing things like Berry-Essing, order 1 over root n. You certainly don't notice epsilon. You really have to make the rate epsilon incredibly small before you start getting a process which is beginning to have more mass on 0 than it ought to have. And in particular, if you have a quasi-stationary distribution, then you can identify it in terms of a return process where at the point when you're going to 0, you transform back into the space according to the distribution, which is in fact itself the quasi-stationary distribution. So it is also one of these return processes. And it's very easy to use this argument to show that that ideal solution is no different from what you get by putting in an epsilon, except at negative exponentially small, e to the minus n small errors. So one feels that Bartlett's intuition was well vindicated. Here's another set of problems. We wrote a paper, this was Richard Aratia, Simon Tavery and myself, with the title Analytic Arithmetic of Algebraic Function Fields, a Probabilistic Approach. We sort of rather like the title because it had got most areas of mathematics in it, apart from geometry. There's a title here. I don't know how many of you know who Tom Lehrer is. Yes, some of you. Good. I'm glad to say that it's not only the really oldies that know of his existence. Cabaretist who wrote, some people say, irreverent songs, or, according to the New York Times, tasteless, for instance. So in his Lobachevsky song, this is title of first original paper that the research student is given to write. And you will see that he has even more varieties of mathematics represented than we had. Actually, those of you who are not only awake at this time in the conference, but also were very attentive, will notice that this name has appeared before in the talk, and that was in the example of the 2k minus 1 dependent process. And it is the same Lehrer. He is a mathematician. He wrote 2 papers somewhere between combinatorics and applied probability. So he will maybe be the most important applied probabilist, or at least the best known. Sorry, let's get this right. Okay, so what's all this about? Well, it's about what happened after I'd written the book on Poisson approximation, and I really wanted to do something that wasn't Stein's method. So Simon said, come and work with him and Richard. They got some problems on polynomials over finite fields, random polynomials over finite fields. So let's just get that. Here's a monic polynomial over a finite field. Let's suppose the field of order q, and it's degree n, and it's monic, so its coefficient there is 1, and then you've got coefficients going back, and you've got q coefficients, and each of those has q values to choose from. So there are n coefficients to choose, and each of those has q values to choose from. So the q to the n monic polynomials of degree n. Now, polynomials break up into factors, and over finite fields, these factors can actually have lots of different degrees. It's not just degree 1 for complex and degree 1 and 2 for real polynomials. You can have irreducible polynomials of all orders. And so we think of those things as being prime, and then Knopfmacher-Zhang formalism, into which the monic polynomials fall, is one in which we have objects, we call it an additive arithmetic semigroup. Objects have a degree, and the degree of a product of 2 things is the sum of the degrees. I think that's probably what the analysis is. There are primes, and so any object can be broken up into primes. So you think of it as irreducible polynomials, they can be broken up into irreducible factors. And Knopfmacher and Zhang were interested in finding out what happened with the analog of arithmetic additive number theory, where you have additive functions. So if you apply a function to such an element, a product of two, then the answer is the sum of f applied to the one and f applied to the other when they're co-prime, that is, their expansions have no common prime factors. So then you have to work out what you're going to do to f of products of primes, and two special cases of one where you just make it f applied to the prime itself, and the second one is f of p to k, is k times f of p. These are things that are well known in regular number theory. Now, Knopfach and Zhang started with their data as the number of objects of degree n, and under certain assumptions, they were able to prove things about how many primes there were. So this is a prime number theorem, and we didn't do anything about that. But in particular, you see that the typical thing is that the number of primes, which is mn, looks like a constant times q to the nth divided by n. So you've got the geometric factor q to the nth divided by n times a constant. Typically, not always, but in some average sense. So we were interested in dealing with such objects, and one of the ways of looking at it is to think about the distribution of f of a randomly chosen element in this space. And this can be expressed as a sum, first over the number of elements in the decomposition of your random element, so prime decomposition, the number of size j, that is the Cn of j, and then if you've got some, what the corresponding values of f are on the pieces that, on the ones that you have. So that depends on which elements, prime elements of size j you happen to have. So I won't go into the distribution of that piece. I mean, you can get at that relatively easily. But it's clear that if you want to deal with this sum in general, then you need to deal with the component structure. That is the number of factors of degree 1, factors of degree 2, factors of degree 3, and so on up to degree n. So that's the key thing to look at. And one of the amazing facts about these combinatorial structures is that you can actually express the joint distribution of these components in terms of the joint distribution of some independent random variables. And the catch is that you have to condition on an event, and the event is that the sum of j times zj is equal to n. So it's equals. So it's a sharp conditioning. It's going to be an event of small probability, and you're going to have to work hard to get this conditional distribution from the original. Now, in the case, if we're looking at these zj as a negative binomial with parameters mj, which remember is normally going to be growing like some q to the j divided by j, and p to the j, and we can have any choice of p, because it happens that because of this conditioning factor, the value of p actually cancels in the conditioning, so it's irrelevant. So the smart thing to do is to choose p to be 1 over q, so that the mj times p to the j is staying more or less constant. It's staying like 1 over j, actually. And that will give you, as it were, the best t 0n to look at. So with that particular choice, your random variables are now the zj's, 0 mostly. They're 1 with probability constant over j, more or less. Remember, this factor, which I've put in for the Poisson ones, is going to go to 1. So we're going to be looking at the sum of j times zj, where zj is mostly 0, but is occasionally 1, with probability about constant over j. And again, if your memories are really good at this stage of the meeting, you remember that Larry Goldstein was talking about this in his talk, and he did a toy example for his things, which was doing more or less the analysis of such creatures. Binomial case. But anyway, if the moral of the story is that if you can handle the distribution of this guy, point probabilities, smartly, then you can prove things like the joint distribution of the small components, if you don't go too big, look like independent, and if you look at the big ones, they look like the Ewan sampling formula, which is what you would get if you had Poissons. So there are nice things to be proved, and the important thing is to have good control over the point probabilities of the these random variables. Now, I think I've got my slides back in the right order. You need to get point probabilities. So that's in itself a tricky problem. So how do you do it? And remember, this was an attempt to do something other than Stein's method, but I couldn't actually see any other method than Stein's method which would give us a hope of dealing with this problem. So Stein's method it had to be. If you look at the Poisson version, where the zj stars are Poisson with mean theta over j, then you have exactly a compound Poisson distribution. And William Lowe and Louis Chen and I wrote a paper on compound Poisson distributions with Stein's method, and we know what a Stein equation looks like, and here's one where I've put in the particular parameters we have in this case. And lo and behold, you see theta times the sum of g of w plus j minus wg of w. And in Larry's talk, he was looking at the continuous version with the Dickman, and this sum becomes an integral. But it's essentially the same character coming up in a discrete setting. And then some rather nice things happen. And the first thing is, if you go back to this equation and take the indicator function of a single point, k, then here you get a sum of indicators of points. You get an interval, indicator an interval. Here you get k times that particular point. So if you think about what that means for the W star, it means that the point probabilities are actually given in terms of interval probabilities. So if you can solve your distributional approximation for intervals, then you can already get point probabilities. So that means we're in business using Kolmogorov distance. So for your general random variable z, you need to show that the expectation of the Stein operator evaluated at your Wn is small, and then you can say things about approximating the point probabilities for that, again by interval probabilities, and you're away. So the only thing that needs doing is to control the solutions of this compound Poisson equation. And there's a general bound for any compound Poisson equation in the paper that Lewis and William and I wrote, and if you plug it in here, you get n to the theta, so it's pretty big. So that's not much use to you. And then there's another bound in the case that j times the intensities are decreasing, and that's satisfied here because they're constant up to n, and then they drop down to 0. But unfortunately, the bound is in terms of the first minus twice the second, and that's 1 over that, I'm afraid. So that's not much use either. So in practice, you have to grit your teeth and take differences and go to the generator method, which the j mu j decreasing does give us. There is a process, there is a generator, and we have the generator of an immigration in clumps and death process, and you can work with that to do the analysis of the solutions. Well, I think that's enough. I mean, it's been a long meeting, and we've had 3 talks today, and we're all going to go home, so I think at this point I'll stop and say thank you for your attention.